So this is the general statement. Sometimes they can ask you to simply define the Kirchhoff's first law or Kirchhoff's current law. This law is based on the principle of conservation of charge. And a very popular question in paper 1 you get from this statement is the Kirchhoff first law based on the conservation of charge, conservation of energy, conservation of current. It is based on conservation of charge. And if you want to write this thing mathematically, we can say the sum of currents into the junction, that would equal the sum of currents getting out of the junction. Now, what is junction? Junction means simply a point in node. It is also called as a node. A point in the circuit where currents combine, where they add up, where they go in different paths. So that is called a junction, that is called a node. So if I am to write the expression for this one, I can see there are two currents, or matter of fact, sorry, three currents that are entering towards the junction, into the junction, to that point, I1, I2, and I3. So you could clearly see three currents are entering in the junction. So the sum of currents entering the junction, this should equal sum of currents leaving the junction. Now, what are the currents leaving the junction? I4 and I5. All right, so far should be so far so good. And the problematic part is when you have to apply these laws in complicated circuits, in complex circuits. So obviously the basics, if you follow the basics, everything else would be just trivial. Then we have up next the Kirchhoff's voltage law, aka KVL. So for this one, there are plenty of statements that you could find about Kirchhoff's second law, but the one that you have to use for the CIE exams is sum of EMFs equals sum of potential differences in a closed loop. So this is what the Kirchhoff's second law says. In other words, you can also say the same thing differently, that the sum of voltages in a closed loop is always zero. So if you mathematically, algebraically add the voltages of the source and the potential drops, so arithmetically it would be zero. So what we can write is the sum of voltages in a closed loop is zero. Up next, we can write the mathematical expression for this one. And this one would simply be the sum of EMFs would equal the sum of potential differences. And lastly, this law is a manifestation of law of conservation of energy, or it is consistent with the law of conservation of energy, because primarily voltage is nothing but energy, work done per unit charge. This is what the voltage is. So EMF or voltage, essentially it is work done per unit charge, so work would be in joules. So it is a manifestation of energy, law of conservation of energy. Now the next thing is, how do we solve the circuits, or how do we apply especially KVL, the second law? How do we apply the second law in a circuit? Because the very popular questions are, you have to form the equations using the KCL or KVL in order to solve the circuit. In some of the questions, they simply ask you to form the equations, nothing else. The question is simply to form the equations using KVL. For example, you could see a question like this. You see, the circuit is not too simple. You may not be very comfortable with the circuit, especially at first sight. And how about this one? Once again, apparently the circuit looks kind of a tricky one, And how about this one? Once again, apparently the circuit looks kind of a tricky one. And this one you have. So plenty of examples, plenty of ways, plenty of combinations they can give. You can never memorize the equations for the circuits because the combination of the circuits can be countless. So it is essential that have you should understand, or you should at least memorize the steps that would be used to form the equations in the circuit. So I'm going to draw a very simple circuit first, and obviously the question won't be that much simple, but just to understand the steps, I'm going to draw a very simple circuit. So I'm going to connect a battery with the resistor, and through the resistor the current would be flowing. So here's the circuit that I'm proposing for the explanation. This is the resistor, and that completes the circuit. As simple as you like. So let's say the EMF of the source is E, and yeah, let's call it E, the EMF of the battery. And the resistance of the resistor is R. The current that flows through the circuit is I. I've not shown the direction of current deliberately. It could be, you can use conventional or you can use the other direction, whatever you want. You can go with that. So, like I said, the direction of current could be totally of your choice. So let's say the direction of current is this. So this one is negative. Obviously, the shorter terminal is negative. The longer terminal is positive. Now, what is the first step? Whenever you have a circuit, then in the first step you have to do is, the very first step is you have to mark one of the batteries, because there could be more than one battery in the circuit. You have to mark one of the batteries as a reference battery. So in this case, the only battery that you have would be your reference battery. But when you get a question, for example this one, you see E1, E2, E3, there are 3 batteries. You have to choose any of it as a reference battery. Or think about this one. You have E1, you have E2. You have 2 batteries. Out of these 2 batteries, you have to choose one as a reference. Likewise, in this one, you have 2 batteries. So you have to mark one battery as a reference. That is the first step. And you need to consider this thing, that there are at least 3 to 4 ways you can solve the circuits. So there are different methods, and pretty much every teacher has a different method, and different books also follow a different method. So I'll try to explain you, give you an introduction of a couple of methods, the most famous one, and then personally I would suggest this one, and then you can adopt any of it. So the first one is mark one battery for your reference, and you have marked the positive and negative. And in the next step, all the components or all the devices that consume the energy, you have to mark their polarities. Polarity means, for example, this resistor has 2 sides, the left one and the right one. But the one that is touching the positive of the battery, you'll mark it positive, and the other one would be marked negative. So the legs of the components would be marked according to the battery, according to that reference battery. So how do we say to that? For the resistors, so resistors, could be any other appliance as well. Any device that consumes the electrical energy. Mark the leg closer to batteries positive as positive. And obviously the other way around. So this side of the resistor would be marked positive because it is touching the positive of the battery. And the other one would be marked negative. I don't need to write the other one. It obviously, the negative one would be marked negative if it is touching the negative side of the battery. The next step, You have to choose any direction of current. You can choose it clockwise or anti-clockwise. You have to choose a direction for the loop. Either you want to go clockwise or anti-clockwise. So choose the direction of loop. It would either be anti-clockwise or clockwise. So how do you want to solve the loop? Either you want to go this way, let's say clockwise, or the other way, anti-clockwise. So for example, in this case, I'm going to go clockwise. I want to go clockwise. Number 4. Now this is the most important one. As you move through the circuit or across the circuit through the components, so different components, if you move from negative to positive, then the voltage across it would be negative. If you move from positive to negative, then the voltage across it would be positive. So as you move across circuit, whatever direction you have chosen, now this is the most important one. If you move from positive through that component, through any component, if you move from positive to negative, the voltage would be treated as positive. And if you move negative to positive, the voltage would be treated as negative. And finally, whatever the expressions are, you put them equal to 0. So these are the steps. Obviously, at this point, it may not be very much clear, like how do we apply these steps. So I'm going to explain all of them with some of the examples. So I'll keep referring to these pointers with each and every question, so you can have an actual understanding how can we use these steps to sort out any circuit, and especially how do you use this one to write the equations for the circuit. So for example, here we have the first question that you can see over here. So the question reads, 3 cells of electromotive force E1, E2 and E3 are connected into a circuit as shown in figure 5.1. The first part is this one. You have to, okay, I just skipped, cropped out some of the some piece of information here. The question was, write down, using the Kirchoff's laws, write down the equations for. This was part of the question. Using Kirchoff's laws, write down the equations for I1, I2 and I3. So you have to relate these 3 currents, I1, I2 and I3. So how do you do that? First of all, you have to use KCL. And in order to apply KCL, you have to choose a junction. You have to choose a point where you can see the currents coming and going out of that point. You have to choose a junction. For example, you can go with this one. Let's say I've chosen this one for the junction Y. Okay. And as you can see, some of the currents are entering the junction and some of the currents are leaving the junction. For example, if I represent I2, this one I2 can also be represented over here. So this one is your I2, and I3 coming from here is just the same. It's just the same. So this one is I3. You can draw over here. And I1 you can see going downwards from the point 5. Now the question is, how many of these currents are entering the junction and how many of the currents are leaving the junction? That's it. All you need to do is you need to find how many currents are entering the junction and how many currents are leaving the junction. So first of all, I'm going to mark the currents that are entering the junction. And matter of fact, that's only I3. Only I3 is entering the junction towards a point. What is the junction? Point Y. Only I3 is traveling there. So I3, sum of currents entering the junction, equal sum of the currents leaving the junction. Now which two are leaving? You have I2 and you have I1. So the sum of currents leaving the junction would be I2 plus I1. So you write it down like this. Good. So this one was an easier one, and obviously KCL is always easier. Now the second one is slightly trickier, at least at the start. But if we follow the steps, keep it in mind, if we follow the steps, it should be easy for us. Once again, there are plenty of ways you can solve the part B. There are different ways. I'll explain both of the methods, but first I'm going to go with the method of what do you call that, the steps. I'm going to follow those steps. So you have to choose a loop W, X, Y, Z, W. This is given in the question. Now you have to choose, you have to apply KCL for this loop. WX, then X to Y, then Y to Z, and then from Z to X. So means the central part, the diagonal, is not part of the circuit, not part of the loop right now. We have to use the outer loop, W, X, Y, Z, and back to W. And we have to relate pretty much everything. You can see if the final expression contains anything other than those mentioned, then we'll have to rearrange it probably. So what is the first step? If I scroll up, the first step is choose a battery as reference. So we have to choose out of two batteries, we can choose a battery as a reference. E2 is not part of the loop. So I hope you won't be inclined towards E2 because that's not even part of the loop. So we have to choose a battery as a reference battery between E1 or E3. So let's say I'll go with E3. Okay, for no specific reason, I'll say just it is closer to the pointer So I'll choose this one as reference. And I can just highlight it. So you can see I've chosen this battery as the reference. That's it. That's the end of the first step. What else do we have? Well, in the second step, we have to mark the legs of the resistors according to this battery. So you see the longer terminal is positive and this one is negative. So the one connected directly to the positive, you see this one would be positive. And for the other resistor, this side is touching positive of the reference battery. We have to mark with respect to the reference batteries once again. Now forget about all the other batteries. This one would be negative, positive. Now this one would be positive, this one would be negative. And for this resistor, this is touching, the upper side is touching negative of the reference battery. So this side would be negative, this side would be positive. And for the batteries, it's obvious that this one is negative, this one is positive. Okay. For batteries, we cannot change the polarity. I have written in the pointer for all the resistors or the current consuming devices. The devices, the appliances that consume the electrical energy. Only those ones. So that's the second step. And what's the next step? Choose direction of the loop, anti-clockwise or clockwise. So let's say I go with this thing clockwise. I've chosen the direction of loop as clockwise. And what else do we have? Yes, now you have to start moving through the components, and just keep it in your mind, if you move from positive to negative, the voltage would be positive. If you move from negative to positive, the voltage would be negative. So let's choose any starting point. You can choose any of the point as starting point. For example, let's say the starting point of the loop I choose to be this one, W. Okay, it could be any other point. You can start the circuit from X or Y or Z, anywhere. But I'm just going with this thing that the loop started from W, and I have to go clockwise. Okay, I'll be going clockwise. So I'm starting from here. This is the start, and I'll be going clockwise. And meanwhile, whatever I have in the circuit, I'll keep writing the voltage drops or the EMFs that I have in the pathway. For example, so I started walking from here, I move upward, and the first potential difference that I get would be across this one. And since you're moving clockwise, so you're moving from positive towards the negative. From positive towards the negative. And the current that was passing through the resistor R3 is I3. You can simply write I3 over here as well, because that is, both of them are in series, the battery and I3. So the current is same. The current passing through the resistor R3 is I3. Now, what is the voltage drop across R3? It is I3R3, because V equals to IR. We have to write the voltages. We never write current only. We never write resistance only. For the second law, for Kirchhoff's voltage law, we always write the voltages, whether it be potential difference, whether it be EMF. So the voltage drop across R3 would be I3. Yeah, it would be I3R3. I3R3, but with the positive sign. Why with the positive sign? Because we're going from positive towards the negative. Okay, so this is the first thing. Now, what is the voltage across the batteries? It's already given. The voltage of the battery, which is also called as EMF, is given as E3. But the question is, do we write it as plus E3 or minus E3? So for this one, yes, you're totally right. We're going to write minus E3, because we are going, first of all, we are going clockwise. And in that direction, we go from negative. Yes, we're going from negative towards the positive side. We were going clockwise, and in our pathway, we are going from negative towards the positive. So this is what the fourth pointer is all about. If you go from negative towards positive, the voltage would be negative. So let's write minus E3. So done till here. And then the next component that we have in the path is this one. And how much current is passing through this one? This one, once again, is in series with the battery, and the same current flows through it, which is I3. So we have passed this point, we have passed this point. Now, we have to write down the expression for the voltage or for the potential difference across R4 for this one now. So since we were going from this side clockwise, and we're going from positive towards the negative, so the voltage would be written with the positive sign. And how much? V equals to IR. I for the resistor R4, the current that is passing through R4 is I3. So we're done with this one. Now we move at this point. Now we take a look at this component. We take a look at this component now. So I3 R4 with the positive sign, we are done with that. And let's move on to the next component. And for this one, you see, once again, first of all, we are moving, since we are moving clockwise, so we are moving from positive towards the negative side. So the voltage would be written with the positive sign, and it would be V equals to IR. And current is I1, the resistance is R1. Done with this one as well. And now we have moved to this point, done with this component, done with all the previous ones. The last component is a source. And for this one, as we go downwards, since we are following clockwise direction, as we go downwards, we move from negative side towards the positive side. We jump from negative towards the positive. So the voltage would be written with the negative sign. And the voltage for the battery is called EMF. So you don't have to write V equals to IR because that's already the value of V. You don't have to write the expression once again. So what do we get? Well, you can shift the negative side, negative things on the other side. They will be positive. For example, if you shift negative E1 and negative E3 on the right side, it would all be positive, and then you'll be left with I3R3 plus I3R4 plus I1 R1. Okay, so that was for the first loop. Now I'm going to erase this one off because we have to now apply the KVL for loop YZWY. So YZWY. So for basically for this right angle triangle. And like I said, there are different ways you can solve them. One of them is to write EMFs on one side, potential differences on the other side of the equation. But today we are just going with this method. And might be in the next lesson I'll introduce the second method as well. But for now we have to apply KVL, but for the loop YZWY. So let me highlight the loop first. So we start from here, go all the way to Z, then for all the way to W, and then all the way back to V. We have to consider this loop. Now everything outside of this loop is irrelevant. So forget about E3, forget about R3, forget about R4, forget about the junction X. These are irrelevant. So what are the steps? Out of the batteries, choose one of the battery as as reference battery. So I'm going, let's say I can choose this one as reference. So once again, it's totally your choice. I have chosen this one as a reference battery. So this one is the reference, and as you can see, this side is negative, this side is positive. Now all the resistors would be marked according to this battery. For example, for the resistor R2, it touches the positive side of the battery, so this one is positive, this one is negative. And for the resistor R1, it touches the negative side of the battery, reference battery, so it would be marked this way. Okay, so their polarity is marked with respect to the reference battery. I keep repeating, it is marked with respect to the reference battery. Up next, you have to choose the direction of the loop. Let's say I want to go clockwise. So I'll sort out the loop clockwise, and I'll be starting off with the point, let's say Y. So I'll start the loop from this point. This is my starting point. So at this stage, I want to erase all the extra arrows and all that. So let us try to apply on this one. Now first of all, as I go downwards over here, the first appliance or the first component that I have is R1, and the voltage across this one would be I1 into R1 with the positive sign. Why with the positive sign? Because the direction of the loop we have assumed is clockwise, and we are moving down the line. So we are jumping from positive towards the negative. And the positive and negatives were marked previously with respect to the reference battery. And we have to follow that polarity now. We have to follow that convention. What do we have after that? Well, up next, we are done with this component. Up next, we have a source. We have a battery itself, but we are going from negative towards the positive. So this one would be written as minus E1. It would be written as minus E1. Okay, so now we are at the point we are at this component R2, which is the most tricky one. If you just pay attention to it, you would not be committing the same mistake again. We are at the point or at the appliance R2, and we are sorting out the circuit clockwise. So we are moving from positive towards the negative. So the potential difference would be positive. And how much potential difference would be there? It would be IR. It would be IR. How much current is there? I2. What is the resistance? R2. So it would be I2 R2. But since we are going clockwise, so we are following this direction, but the direction of current through the resistor is opposite to the direction of our loop. So the I1 would now be written as minus I2 into R2. Or in other words, what you can do is, if this is I2, since you're following the clockwise direction, but this current is kind of going anti-clockwise. It's going like in this way. If you want to convert it into clockwise, so all you have to do is just replace I2. You change the direction of it, and then it would be minus I2. So this is what we have done. I2 would be replaced with minus I2, and this is then consistent with our direction of the loop. So once again, you'll be getting plenty of questions in which you'll have to reverse the direction of current, and hence you'll have to reverse the sign for the current, and this one minus I2 R2. And for the last component, which is the battery itself, you see this one is positive, this one is negative. For the batteries, we cannot change the polarity. The longer terminal is always positive, and we are going clockwise. So as we move on this side, we are going from positive side towards the negative side. So this one would be written with the positive, and all of it equals to 0 because we have completed the circuit. So how do you simplify this? I mean, if you want to simplify, you can. Otherwise, it's just optional. Minus E1, and then it would be minus I2 R2 plus E2 equals 0. If you want to put the things on the right side, the negative ones, you can. Once again, I'm saying it's just an optional thing. For example, I can write it as E2. Let's write sources on one side. E2 minus E1. These are the EMFs, and if you shift this thing and this one on the right side, it would be I2 R2. It would be changed to positive, and this one would be changed to negative I1 R1. So this is one of the method that we use to apply KVL.